In this video, we introduce the three main implementations of the simplex method, which are the naive implementation, the revised simplex method, and the full tableau implementation. Before we start, it's very important that you remember the description of an iteration of the simplex method which we saw in section 3.2. It is clear from the statement of the algorithm that the vectors B inverse AJ play a major role. In fact, they appear several times in the algorithm. First, they appear when we compute the reduced cost C bar j. In fact, here we have B inverse AJ. Then, when we compute the vector u or minus u, since the vector u is defined to be exactly B inverse AJ. Finally, B inverse AJ plays a key role also in the computation of the step size. Here, B inverse AJ appears implicitly in a sense because in the minimum we have in the denominator ui. Now, the main difference between the alternative implementations that we're going to see lies in the way that the vectors B inverse AJ are computed. Another related difference lies in the amount of information that is carried from one iteration to the next. Because as we will see, in order to compute B inverse AJ more quickly in the next iteration, it will be useful to carry over some information from the previous iteration. Before starting with the analysis of the naive implementation of the simplex method, let me remind you a few important facts that we need to keep always in mind in order to be able to quickly compute the number of arithmetic operations required by each implementation. Let's say that capital B is a given m by m matrix, and let's say that B and P are given vectors in Rm. Then, whenever we need to compute the inverse of B, or if we need to solve a linear system of the form capital Bx equal to B, this takes big O of m cube arithmetic operations, as we have seen in section 1.6. On the other hand, if we need to compute the matrix vector product capital B, B, this takes O of m square operations. Finally, if we only need to compute an inner product P transpose B, this takes O of m arithmetic operations. We are now ready to dive into the naive implementation of the simplex method. This is by far the most straightforward implementation. Essentially, we will go through an iteration of the simplex method as seen in section 3.2, and while doing so, we keep track of the number of arithmetic operations that we need to perform. At the beginning of a typical iteration, we have the basic indices b1 until bm of the current basic feasible solution. The next step in our iteration of the simplex method is that of computing the reduced costs. However, here we take an intermediate step. In fact, in the definition of the reduced costs, the quantity CB transpose B inverse appears, and it appears exactly the same in all the reduced costs. So it makes sense to compute first this vector, so that later we don't need to compute it again and again for every reduced costs. Now we're gonna give this vector the name P transpose, and from now on we're gonna use this vector several times. And this is called the vector of the simplex multipliers associated with the basis capital B. So how long does it take to compute the vector P transpose? From this equality we can multiply on the right by capital B and obtain the system of linear equalities P transpose B equal to CB transpose. This is a system of m equality constraints in m variables. So as we have just seen, it takes big O of m cube operations to find the vector P. Now we're ready to compute the reduced costs. Our formula for the reduced costs is C bar j equal to Cj minus Cb transpose B inverse Aj. Now that we have calculated the vector of simplex multipliers, we can substitute Cb transpose B inverse with P and obtain this simpler formula. So how many operations now it takes to compute one reduced cost C bar j? The first thing we need to do is compute the inner product P transpose Aj. These are two m vectors, so it takes a big O of m. Then we only need one more operation, which is this subtraction. So in total we have a big O of m operations to compute one reduced cost C bar j. However, we need to compute the reduced costs of all the variables xj. Therefore, in total, we need n times big O of m operations, and this is big O of mn. Before proceeding, let me make a couple of remarks about the reduced costs. The first is that in a specific iteration of the simplex method, you may not need to compute all the reduced costs C bar j. For example, if you're using the smallest subscript rule and the very first reduced cost that you find is negative, then you don't need to compute all the other ones. However, remember that we're looking here at the worst case number of operations. And in the worst case, no matter which pivoting rule you use, you might be unlucky and there might exist only one negative reduced cost, and this is the very last that you compute. So in general, no matter which pivoting rule you use, you might have to compute all of the reduced costs. So essentially, considering a specific pivoting rule here doesn't give you any better runtime. Now, the second remark that I want to make is that we know already that the reduced costs of the basic variables is always 0. So we don't really need to compute the reduced costs for the basic variables. We can just focus on the non-basic variables. Accordingly, to compute the reduced costs of only the non-basic variables, we only need n minus m times big O of m operations. However, this product still gives us big O of mn operations. Therefore, this simplification doesn't give us any better runtime asymptotically. Once the reduced costs are computed, then, according to our pivoting rule, we select the column aj that should enter the basis. Our next task is then that of computing the vector u that we know corresponds to the jth basic direction. The definition of the vector u is b inverse times aj. So in order to compute u, we can multiply on the left this system by b inverse and obtain the linear system bu equal to aj. This is a system with m variables and m constraints, and so we can obtain u in a big O of m cube operations. The next step in our simplex method is that of computing theta star, which tells us how far along the jth basic direction we're supposed to travel. The definition of theta star is the minimum of xbi over ui for I that ranges from 1 to m with ui strictly positive. At this point we have all the xbi's available and we have computed all the ui's, so with at most m operations we can compute all these ratios. And then with essentially m more comparisons, we can find the one that is the smallest. And so we can compute theta star. So in total, theta star can be computed with big O of m operations. The index that gives us the minimum also tells us which is the variable that will exit the basis. And this allows us to construct the new basic feasible solution and to terminate this iteration of the naive implementation of the simplex method. So what is the total number of arithmetic operations that we performed in an iteration of the naive implementation? We needed big O of m cube operations to compute the vector of the simplex multipliers, then big O of mn to compute all the reduced costs, then big O of m cube to compute the vector u, and finally big O of m operation to compute theta star. Since m is in big O of m cube, this is simply big O of m cube plus mn. One of the great advantages of the naive implementation is that what we're doing is extremely clear from a geometric point of view. In fact, in the naive implementation, we have just followed our construction of the simplex method that was based from the very beginning on our geometric intuition. So the naive implementation is easy to follow and understand. One of the drawbacks of the naive implementation is that it is rather inefficient. In fact, in the next implementations that we will see, the runtime will be big O of m square plus mn. So in particular, we replace the m cube with an m square in the runtime. So let's see the revised simplex method, which will allow us to achieve this runtime. To be able to replace the m cube with the m square in the runtime, we need first to understand where this m cube comes into play. And it comes into play in two specific points in our implementation. Namely, when we compute the vector p from the system p transpose b equal to cb transpose, and when we compute the vector u using the system bu equal to aj. The main idea behind the revised simplex method is to notice that in both these systems, the matrix B plays a key role. In fact, if we had available the matrix B inverse, then we could compute both vectors P and U much more quickly. In fact, if we multiply the first system by B inverse on the right and the second system by B inverse on the left, then we would obtain that P can be calculated as the product CB transpose B inverse, while the vector U can be computed with the matrix vector multiplication B inverse AJ. So to obtain either P transpose or U, we only need to compute a matrix vector multiplication where the matrix is M by M and the vector is in Rm. And we know that this multiplication can be performed in only O of m square operations. So this idea gives us a clear path on how to decrease m cube operations to m square operations in a single iteration. However, the main difficulty here is that we don't in fact have the matrix B inverse. And if we wanted to compute B inverse starting from B, it would take us again m cube operations. And so we would obtain once again the same running time of the naive implementation. So in order to obtain this better runtime in the revised simplex method, we need a smart way to construct a B inverse at each iteration that doesn't require m cube operations. Why should we be able to do this? What is the idea behind this? Well, everything starts from a very simple observation. Namely, that the basis matrix B doesn't change very much from iteration to iteration. In fact, at the beginning of our iteration, B is equal to AB1, ABM, our m basic columns of the constraint matrix A. Now at the beginning of the next iteration, the basis matrix that we now call B bar is almost the same. We only replaced one column, namely ABL, with AJ. So B and B bar are almost the same. There's only one column that is different. It is then reasonable to expect that also the inverse of B is not so different in some sense from the inverse of B bar. And so the idea is to use B inverse to quickly obtain B bar inverse without needing to compute B bar inverse from scratch, which would require m cube operations. How exactly are we going to compute B bar inverse efficiently? The first thing that we're going to do is to observe that B inverse times B bar is not very different from the identity matrix. And this is because, as we have just observed, B bar is not very different from B. And of course, B inverse times B is equal to the identity. Now, since this product is not very different from the identity, we can compute a new matrix that we're going to call Q, such that Q times the product B inverse B bar is equal to the identity. And once we've done this, we're done, because then Q B inverse will be the inverse of B bar. So this is the roadmap that we're going to follow to compute B bar inverse efficiently. So let's get back to the first step and compute B inverse B bar. Of course, B inverse times B is equal to the identity. And now, if we look separately at all the columns of B, we obtain that B inverse times ABI is equal to EI for every I that goes from 1 to m. Now we can finally look at the product B inverse B bar. Now, except for the column L of B bar, all the other columns are the same as those of B. Therefore, in this product, the first column will be A1, the second E2, and so on and so forth until EM at the very end, except for the column L, and the column L of the product B inverse B bar will be B inverse times the Lth column of B bar, which is AJ. Therefore, such a column will be exactly our vector u. So here on the right we can visualize this matrix. As you can see, it is the identity matrix, but where the nth column is this vector u, with components u1 until um. So we've now understood exactly how the product B inverse B bar is not very different from the identity matrix. The next thing we want to do is compute a matrix Q such that if we multiply this matrix B inverse B bar on the left by Q, we obtain exactly the identity matrix. In order to obtain the identity matrix by multiplying on the left by Q, we need to introduce elementary row operations. These are defined as the operations of adding a constant multiple of one row to the same or to another row. The nice thing about elementary row operations is that they can be obtained by multiplying on the left by a suitably constructed square matrix. Let's start with an example. Let's say we have a matrix C, this matrix over here, and we multiply it on the left by this matrix Q, which is obtained from the identity by replacing this element with a 2. Let's just compute the product QC and see what we obtain. Now the second and third rows of QC are exactly the same rows of C. This is because the second and third row of Q are simply rows of the identity matrix. So if you make this computation, you obtain 3, 4, 5, 6, exactly like here, 3, 4, 5, 6. So things change only in the first row because it's different from the original row of the identity matrix. So let's compute now the first row of Q times C. In the first column, we will have 1 times 1 plus 2 times 5, which is written over here. While in the second column, we will have 1 times 2 plus 2 times 6, which is written over here. So to summarize, the first row of QC is equal to the original first row of C. You see the 1 and 2 over here, match the 1 and 2 over here, plus 2 times, which is the coefficient here, 5 and 6, which correspond to the third row of C. So overall, multiplying the matrix C on the left by Q had the effect of multiplying the third row of C by 2 and adding it to the first row. In our matrix Q, the number 2 here is in the first row and third column, and this implies that we modified the first row of C using the third row of C. So while the value of this entry tells you the factor in this addition, on the other hand, the position of this entry 2 tells you which row of C will be modified, in this case the first, and using which other row, in this case the third. Now let's generalize this example. You can show that if you want to multiply the jth row by a scalar beta and you want to add it to the ith row, then this can be achieved by multiplying your matrix on the left by the matrix obtained by summing the identity with the matrix Dij, and Dij has all entries equal to 0 except for the entry in row I and column j, which will be equal to beta. In the previous example, we had that I was equal to 1, j was equal to 3, and beta was equal to 2. A key property of this matrix Q is that it is invertible. To see that, we need to assume that I is different from j, which implies that the diagonal of Q has all 1 entries, and therefore the determinant is 1. We will be interested in applying a sequence of a number k of elementary row operations. Now let's say that the kth operation corresponds to the left multiplication by matrix Qk. Then the sequence of elementary row operations can be obtained by multiplying on the left by Qk times Qk minus 1 and so on and so forth until Q1. And this is simply because you start from your matrix, you first multiply on the left by Q1, then by Q2, and so on and so forth. You keep multiplying on the left by the next matrix Qk. Since all these matrices are invertible, then so is their product. So also performing a sequence of elementary row operations is equivalent to left multiplying by a certain invertible matrix. Now we will see how we can use these elementary row operations to compute B bar inverse starting from B inverse. We have already seen that B inverse times B bar is this matrix over here, which is obtained from the identity by swapping the lth column with the vector u. Our task now is to perform elementary row operations on this matrix to obtain the identity. In order to be able to do this, it's fundamental to recall that UL, which is the entry of the U vector which is on the diagonal, is strictly positive. And this follows from the definition of theta star. Using this property, we can now proceed to zero out all the entries in the column except for UL. For example, how can we transform U1 into a 0? Everything we need to do is to pick the row L, multiply it by minus U1 over UL, and in this way we obtain a row that is 0 everywhere except for the lth entry, which will be equal to minus U1. At this point, if we sum it to the first row, we obtain the row that is 1 in the first entry and 0 everywhere else, which is exactly what we wanted. Similarly, for every row I different from L, we add the lth row times minus ui over ul to the ith row, and this has the effect of replacing ui by 0. After all these elementary row operations, we still have to deal with the row L. And everything we need to do is to divide the row by ul, so that the entry ul becomes 1. Note that we never talked about elementary row operations where you divide a row by a number. You should check that this is also an elementary row operation. And it is a little bit different from the other ones that we've seen so far, because you're essentially adding a multiple of a row to the same row. In particular, for an elementary row operation of this type, we didn't check that the corresponding matrix is invertible, so I leave this to you. So we have understood how, with elementary row operations, we can replace the lth column u by the lth unit vector el. We know that this is equivalent to multiplying on the left B inverse B bar by a certain invertible matrix Q. So, as we have already discussed, the matrix B bar inverse, which is our target, will be equal to Q B inverse. In particular, this identity tells us that the matrix B bar inverse can be obtained from B inverse by applying the same sequence of row operations corresponding to the matrix Q. Therefore, all the elementary row operations that we needed to transform the column U into the vector EL. So now we have fully understood how to construct a B bar inverse starting from B inverse. So the next question is what is the total number of arithmetic operations? Obviously, we can find all the factors minus ui over ul with only big O of m operations. However, when we apply the corresponding m elementary row operations to the matrix B inverse, we will perform a constant number of operations for every entry of B inverse. Therefore, in total, we will perform big O of m square operations. Now let's see an example where we have a matrix B inverse, we have the vector u, and we have the index L, and we want to construct a B bar inverse. We start by looking at the matrix B inverse B bar. This is obtained from the identity matrix by replacing the column L, so the column 3, and here we have such a matrix. Therefore, our objective is to transform the vector u into the unit vector E3, which is 0, 0, 1. Next, we want to replace the minus 4 with the 0. To do that, we simply need to pick the third row, multiplied by 2 and added to the first row. Next, we want to replace this 2 by a 0. In order to do that, we multiply the third row by minus 1 and add it to the second row. Finally, we want to replace this 2 by a 1, and everything we need to do is divide this row by 2. Now these three operations are written here, And the next thing we want to do is apply the same 3-row operations to B inverse, and this will give us B bar inverse. So then let's look at B inverse and let's multiply the third row by 2 and add it to the first row. The third row multiplied by 2 is 8 minus 6 minus 4, and if we add it to the first row, we obtain 9 minus 4 minus 1. If you perform also the other two elementary row operations, you obtain also the second and third row of B bar inverse, which should be the ones written here. And this concludes our example. At this point, we know how to update the matrix B inverse from iteration to iteration in our simplex method. And this only takes us big O of m square operations per iteration. The revised simplex method is then obtained from the naive implementation by making this change, namely by updating B inverse at every iteration as described and using it to obtain the vector of the simplex multipliers and the vector u. Now let's see a full iteration of the revised simplex method. Again, it is very similar to the naive implementation, so I'm going to highlight in blue the differences. We start with the basis, consisting of the basic columns AB1 until ABM. Then we have the associated basic feasible solution X and the inverse of the basis matrix B inverse. Now we can compute the vector P of the simplex multipliers using the formula P transpose equal to CB transpose B inverse. And in turn, we can use the vector P to compute all the reduced costs, C bar j equal to Cj minus P transpose Aj. If all the reduced costs are non-negative, then the current basic feasible solution is optimal and the algorithm terminates. Otherwise, we choose some j for which C bar j is negative. Next, we compute the vector u, and now we can simply compute it with the formula B inverse Aj. If no component of u is positive, we know that the optimal cost is minus infinity and the algorithm terminates. Otherwise, some component of u is positive, and we calculate theta star as the minimum of the xbi over ui over all I from 1 to m with ui strictly positive. We denote by L the index which achieves the minimum in the definition of theta star. So theta star is equal to xbl over ul. We form the new basis by replacing ABL with AJ, and we denote by Y the new basic feasible solution. The basic components of Y can be easily computed with Yj equal to theta star and Ybi equal to xbi minus theta star ui for I different from L. At this point in the naive implementation we were done. However, in the revised simplex method, we need to compute the inverse of the new basis matrix, which we denote as always by B bar inverse. And this is because we're going to need this matrix in the next iteration. We can write in several ways how to obtain B bar inverse. Here I'm going to do it in a little bit different way from what we've seen so far. It will be clear that it's equivalent and it's a little bit more compact to write down. We form the M times m plus 1 matrix obtained from B inverse by appending the vector u. We add to every row of this matrix a multiple of the lth row to make the last column equal to the unit vector EL. Once we have done this, the first m columns of the resulting matrix is exactly B bar inverse. Let's now analyze the runtime of an iteration of the revised simplex method. So we once again go through the iteration, but we explicitly write down all the arithmetic operations that we perform. So at the beginning of our iteration, we have our basic indices B1, Bm, and the matrix B inverse, which has been calculated in the previous iteration. Now we can compute the vector P transposed using the formula CB transpose B inverse, and this only requires big O of m square operations, because it's just the product of an m vector times an m by m matrix. Then we compute the reduced cost C bar j using the formula C bar j equal to Cj minus P transpose Aj. To compute each C bar j, we only need big O of m operations, because it's an inner product and one subtraction. However, we need to compute n of them, so in total we obtain big O of mn operations. Next, our pivoting rule decides what is the column aj that should enter the basis. Then we need to compute the vector u, and we compute it using the formula B inverse aj. Also here, this is simply the product of an m by m matrix times an m vector. So u can be obtained with O of m square operations. Then we compute theta star, as always using the formula min of xbi over ui over all I from 1 to m with ui positive. Like in the naive implementation, this takes a big O of m operations. Now we know what is the variable that exits the basis, and we can construct the new basic feasible solution and the new basis matrix B bar. Finally, we need to construct the inverse of B bar, and we've seen that this can be done in big O of m square operations. So for the revised simplex method, the running time is big O of m square to obtain the vector p, plus mn to obtain the reduced costs, plus m square to obtain the vector u, plus m to obtain theta star, and plus m square to obtain the matrix B bar inverse. This simply is big O of m square plus mn, which is what I promised you we would have obtained. Recall that the naive implementation required big O of m cube plus mn. So clearly the running time of the revised simplex method is better. Finally, notice that big O of m square plus mn is simply big O of mn. This is because, since we're assuming that the rows of A are linearly independent, we always have that m is less than or equal than n. Therefore, m square is less than or equal to mn. For now, this concludes our discussion on the revised simplex method. The main advantage of the revised simplex method is that it is the fastest among the three implementations that we discuss in this course. Next, we introduce the third and last implementation that we will see, and this is called the full tableau implementation. The main advantage of the full tableau implementation is that it will allow us to perform all the computations required in a single iteration of the simplex method in just one table. So this will allow us to visualize very compactly a single iteration of the simplex method. And for this reason, we will keep using the full tableau implementation throughout the rest of the course. Even though the full tableau implementation will be from now on the main one that we will discuss, you're definitely not allowed to forget about the naive implementation and the revised simplex. I think that the main danger with the full tableau implementation is to forget all the geometric intuition that allowed us to truly understand one iteration of the simplex method. So even though you will become familiar with the full tableau implementation very soon, and you will be able to perform all the associated computations, you should always remember what every number in the tableau actually means and where it comes from. Otherwise, you will quickly get lost in our discussions. The main idea of the full tableau implementation is to maintain at each iteration the matrix that is the product of B inverse with the matrix whose first column is B and whose remaining columns is A. This means that the first column is capital B inverse B, the second is B inverse A1, and so on and so forth until B inverse AN. Note that, as opposed to the revised simplex, here we don't have B inverse explicit in each iteration, but we instead have the product of B inverse with all the columns of A and with the right-hand side vector B. This big matrix, B inverse times BA, is called the simplex tableau. Now let's see more in detail this simplex tableau and let's introduce some notation. The very first column of our tableau is B inverse B. This column is very different from the others and is called the 0th column. Recall that B inverse B is the formula that gives us XB. Therefore, the 0th column contains the values of the basic variables of our current basic feasible solution. This means that the 0th column has entries xb1 until xbm. So this column tells us everything we need to know the current basic feasible solution. In fact, the components that are not written here are the non-basic ones that we know are set to 0. The remaining columns of the simplex tableau are B inverse A1, B inverse A2, and so on and so forth until B inverse AN. We will refer to these columns as the first column of the tableau, the second column of the tableau, until the nth column of the tableau. So B inverse AI is called the ith column of the tableau. One of these columns plays a very special role. In fact, we know that B inverse AJ is equal to our famous vector U. This column is so special that we call it the pivot column. In particular, the pivot column also indicates what is the variable that enters the basis. In fact, if U is defined as B inverse AJ, it means that the variable xj is entering the basis. So what about the variable that instead exits the basis? As always, we denote the variable that exits the basis as the lth basic variable. Correspondingly, the lth row of the tableau is called the pivot row. So here in green we have our pivot row, and it corresponds to the variable that exits the basis. Now we have a pivot column and a pivot row, and there's a unique element at the intersection of them, and this is called the pivot element. By construction, this is the entry UL of the vector U. We already know that this element is very special. In fact, it follows from the definition of theta star, or of L, that UL is always positive, unless the termination conditions in step 3 are met, which tell us that the problem is unbounded. Next, we're going to see a very useful interpretation of the full tableau. Remember that in our original linear programming problem, we're given the equality constraints Ax equal to b. Now pick our current basis matrix P, which we know is invertible, and multiply the system of equations on the left by B inverse. We obtain this system. B inverse B is equal to B inverse Ax. Now the coefficients of this system of equations is exactly our simplex tableau. Now, if at the beginning of our iteration this is the simplex tableau, it means that at the beginning of the next iteration, the simplex tableau will be instead B bar inverse times BA. Here it is. Therefore, everything we need to do in an iteration of the full tableau implementation is to update our tableau from B inverse BA to bar B inverse BA. Given what we have understood in the revised simplex, this is very easy. In fact, we know how to transform B inverse into bar B inverse by multiplying on the left by our matrix Q. So everything we need to do to correctly update the tableau is to multiply on the left by the matrix Q that we already discussed in the revised simplex method. And we've seen that this is the same as performing the elementary row operations on the tableau that turn B inverse into B bar inverse. If you remember, these were the operations needed to transform the U vector into the unit vector EL by adding to each row multiples of the lth row. Now, with the notation introduced in the full tableau implementation, the U vector is the pivot column, while the lth row is the pivot row. Therefore, our elementary row operations can be stated as follows. We add to each row a multiple of the pivot row to set all entries of the pivot column to 0, with the exception of the pivot element, which is set to 1. So you see how we are rephrasing the operations that we need to perform inside the full tableau. Similarly, let's see how we can rephrase in our full tableau the determination of the exiting column ABL and the step size theta star, which are performed in our steps 4 and 5. Now, theta star is defined as the minimum of the xpi over ui's. And now xpi can be found in the tableau in the 0th column in row I, while ui can be found in the pivot column in the same row I. Now, in the definition of theta star, we're not considering all of these ratios, but only those which have a ui that is positive. And again, the ui can be found in the pivot column. Now, the smallest ratio that defines theta star determines L, which is then our pivot row. We have just seen how many important quantities that we consider in a specific iteration of the simplex method are present in the tableau. However, there still are some very important quantities that are not to be found inside the tableau. In particular, the current cost of the solution is not present in the tableau, and, maybe more importantly, neither are the reduced costs. To fix this, the next thing we're going to do is add one additional row to our tableau that will contain these informations. And this additional row will be put on top of the current tableau and will be called the 0th row. At the top left corner, we put the negative of the current cost. So the formula is minus CB transpose XP, or in a different form, minus CB transpose B inverse B. Now, a natural question is why aren't we instead just writing the current cost instead of the negative of the current cost? This is a great question, and the reason we're looking at the negative is in a sense technical. In fact, we will see shortly that having the negative allows us for a much simpler update rule. Then, in the remaining part of the 0th row, we write the reduced costs. So in the first column, we will have C bar 1, then C bar 2, and so on and so forth until C bar n. Once again, the formula for the reduced cost is C bar transpose equal to C transpose minus CB transpose B inverse A. Now we had just understood how we can update the tableau from iteration to iteration. But now we added one additional row to the tableau, and so we need to understand how such a row should be updated from iteration to iteration as well. Now the great thing about the 0th row is that the update rule turns out to be identical to the rule used in the remaining part of the tableau. Namely, we need to add a multiple of the pivot row to the 0th row to set the reduced cost of the entering variable to 0. Of course, we need to prove that this update rule produces the correct 0th row for the next iteration. So it needs to update correctly the negative of the current cost and the reduced costs. Now we're going to prove that this update rule is correct, and we're going to do this in a couple of different steps. Let's start by looking at the 0th row at the beginning of our typical iteration. The entry in the 0th column is the negative of the current cost, which is minus CB transpose B inverse B. The remaining components are the reduced costs, which are C transpose minus CB transpose B inverse A. So this is my row vector representing the 0th row. You can immediately see that minus CB inverse appears in all columns of this vector. So we can factor it out and write this row vector as 0 C transpose minus CB B inverse times BA. At this point, I don't really care so much about what is this quantity over here. What is important is that this is just a row vector. So in particular, I can say that the 0th row is equal to 0 C transpose plus a linear combination of the rows of BA. The coefficients of such a linear combination is given by the entries of this row vector. Now, what I want to show to you in this slide is that after performing the elementary row operations, in the 0th row, we will still have a similar structure. Namely, the 0th row will be, again, 0 C transpose plus a linear combination of the rows of BA. The difference is that the linear combination will be different, but this overall structure of the 0th row will be the same. So how can we see that? As always, the pivot column is column J, while the row L will be the pivot row. Now it follows from the interpretation of the tableau that we have seen few slides ago that the pivot row is of the form H transpose times BA, where H transpose is the lth row of B inverse. In our elementary row operations, we are adding a multiple of the pivot row to the 0th row. So now in total we will have 0 C transpose minus a linear combination of the rows of BA plus a multiple of another linear combination of the rows of BA. So this simply is 0 C transpose plus some linear combination of the rows of BA. Once again, at this point, I don't care about what linear combination this is. Let me just denote the coefficient of such a linear combination by P transpose. So at the end of our iteration, the zeroth row will be 0 C transpose minus P transpose BA for some vector P. So let's recap what we've just understood. At the beginning of our iteration, the zeroth row is 0 C transpose minus CB transpose B inverse BA. And at the end of the iteration, it is 0 C transpose minus P transpose BA. What we have to do now is understand what P is using our update rule and check that we obtain what we should, namely C transpose B bar inverse. In order to prove this, we will explicitly understand how the zeroth row will look like after we have performed our elementary row operations. More specifically, we will look at the column of the zeroth row that corresponds to the basic variables b bar 1 until b bar m. For this entry of the zeroth row, we will be able to understand exactly how the zeroth row will look like at the end of our iteration. So after having applied our update rule. In this way, we will obtain a system of linear equations that will allow us to show that P transpose is equal to CB bar transpose B bar inverse. So let's start with our first case when we consider the column B bar L of the tableau. Now, B bar L is simply a more complicated way of writing J. In fact, remember that the index B of L left the basis and it's replaced by J. So B bar L is equal to J. So the column B bar L of the tableau is our pivot column. So what happens in these columns of the zeroth row once we apply our update rule? The update rule says that the pivot column entry of the zeroth row should become 0. This means that the index B bar L of the formula we computed in the previous slide should be equal to 0, namely C B bar L minus P transpose A B bar L equal to 0. So in this first case, we were able to obtain this equation. Let's remember this equation and proceed to the next case. Next, we consider the columns B bar I of the tableau for I different from L. In this table, we visualize this column over here. And note that this is the table at the beginning of our iteration. Note that this column corresponds to a basic variable that stays in the basis. In other words, we have that B bar I is equal to BI. Therefore, in our column, we can just replace B bar I with BI. So these columns corresponds to a variable that was basic also at the beginning of the iteration. Therefore, its reduced cost at the beginning of the iteration was 0. So we can now replace this C bar BI with a 0. Actually, we know much more about the columns corresponding to basic variables. In fact, at the beginning of the iteration, our column BI is B inverse ABI, which we know is the ith unit vector. So let's write it down here in our column. The only question is where is the 1? Of course, the 1 appears in the row I. And everything I need to observe at this point is that the row I is different from the row L, just because we're assuming that I is different from L. Therefore, this one will be somewhere in this column, but not in the pivot row. And this implies that in the pivot row, the entry of this column will be 0. Now we've understood everything about our column B bar I, and we can now understand the effect of our elementary row operations in the zeroth row. In fact, in our elementary row operations, we add a multiple of the pivot row to the zeroth row. But this means we're not making any change because we're adding a multiple of 0 to 0. So at the end of the iteration, we will still have a 0 over here. In formula, for I different from L, we have C B bar I minus P transpose A B bar I equal to 0. Now this system of equations is the result of our second case, or case B. So now we're ready to put together the results of our cases A and B. Putting together all the equations obtained in these two cases, we have that C B bar I minus P transpose A B bar I equal to 0 in any case, so for I equal 1 until m. We can now write nicely all these constraints in matrix form, C B bar transpose minus P transpose B bar equal to 0. And this is because B bar has columns A, B bar, I. Now we can solve this system by simply multiplying on the right by B bar inverse, and we obtain P transpose equal to C B bar transpose B bar inverse. And this is exactly what we needed to obtain. So with our update rule, the updated 0 row has the form 0C transpose minus P transpose BA, as we have seen a few slides ago, and now we can replace P transpose because we have just understood exactly what P transpose looks like, and we obtain that the 0th row at the end of the iteration is 0C transpose minus C B bar transpose B bar inverse BA, as it should be. And this completes our proof that the 0th row gets updated correctly with our update rule. We're now ready to summarize a full iteration of the full Tableau implementation. Also in this case, one iteration is very similar to an iteration with the previous implementations, so in blue I highlight the main differences. In a typical iteration, we start with the tableau associated with the basis matrix B and the corresponding basic feasible solution X. Now we need to look at the reduced costs, and these reduced costs are in the 0th row of the tableau. As always, if they're all non-negative, the current basic feasible solution is optimal and the algorithm terminates. Otherwise, we choose some j with the C bar j negative. Next, we need to consider the vector u defined by B inverse aj. Now this vector is conveniently placed in the jth column of the tableau, and this is the pivot column. If no component of u is positive, the optimal cost is minus infinity and the algorithm terminates. Otherwise, for every I with ui positive, we compute the ratio xpi over ui. Recall that every ratio can be obtained from a specific row of our tableau. So we let L be the index of a row that corresponds to the smallest ratio. Then the column ABL exits the basis and the column AJ enters the basis. Finally, we need to update our tableau. To do this, we use our update rule. So we add to each row of the tableau a constant multiple of the lth row, which is the pivot row, so that UL, which is the pivot element, becomes 1 and all other entries of the pivot column become 0. Now that we've seen in detail an iteration of the full Tableau implementation, let's immediately see an example. This is the linear programming problem that we consider in this example. So we minimize minus 10x1, minus 12x2, minus 12x3. The constraints are x1 plus 2x2 plus 2x3 less than or equal to 20, 2x1 plus x2 plus 2x3 less than or equal to 20, 2x1 plus 2x2 plus x3 less than or equal to 20, and x1, x2, x3 greater than or equal to 0. This problem has 3 variables, and so we can visualize it nicely in dimension 3. You can find above the corresponding picture. The nice thing about this example is that on the one hand we can visualize it nicely, so we can guess what we want to do in the simplex method, and on the other hand we're going to work out all the algebraic details, and so we will constantly see what we're doing both from a geometric and algebraic perspective. By drawing this example, we can immediately understand which are the vertices of the polyhedron, and we can also easily understand what is the optimal solution. In particular, we are able to understand that the vertices of this polyhedron are the origin, then the three vectors 10, 0, 0, 0, 10, 0, and 0, 0, 10, and finally the vertex 4, 4, 4. By visualizing the objective function as well, it's easy to guess that the optimal solution is the vector E. Now in this example, we will fully solve this linear programming problem using the full tableau implementation. Recall that at this point we're not able to run the simplex algorithm on any linear programming problem. And this is because we don't know in general how to obtain a basic feasible solution to start with. However, in this specific example, we will be able to easily find a basic feasible solution to start with. The first thing that we should observe in this example is that this problem is not in standard form. In fact, while I have all variables non-negative, the problem is that the remaining constraints are not equality constraints, but they are inequality constraints. However, we know how we can transform easily this problem in standard form. Namely, we need to introduce slack variables. In fact, we add one slack variable for every constraint, plus x4 for the first, plus x5 for the second, and plus x6 for the third, and we add the constraint that all these slack variables are greater than or equal to 0. The problem that we have obtained is now in standard form, and we know it is equivalent to the original one. Now, for this standard form problem, it's very easy to obtain a basic feasible solution. In fact, if you set all the original variables to 0, you obtain x4 equal to 20, x5 equal to 20, and x6 equal to 20. This is a basic solution because the three columns corresponding to x4, x5, and x6 are linearly independent. Furthermore, this is a basic feasible solution because it is greater than or equal to 0. So we can use it to start the algorithm. Accordingly, the first basic index is 4, the second basic index is 5, and the third basic index is 6. Clearly, the basis matrix that we obtain is the identity matrix, because that is the submatrix of the new constraint matrix corresponding to columns 4, 5, and 6. Our target now is to construct the initial tableau. Therefore, we need the inverse of the basis matrix, and in this case it's super simple because it's again, of course, the identity matrix. At this point, we know how to construct most of the initial tableau. In fact, we can fill in the entries of the initial tableau everywhere except in the 0th row. In fact, in the remaining rows, we only need to write B inverse times the matrix AB of the coefficients of this system. Since B inverse is the identity, we can just copy-paste all the coefficients of these constraints. Let us now compute the 0th row. In the top left corner of the tableau, we have the negative of the cost of the solution. Now the cost of the solution is CB transpose XB, but now CB is 0 because the variables x4, x5, and x6 do not appear in the objective function. Therefore, at the intersection of the 0th row and the 0th column, we will have a 0. So we only need to figure out now the reduced costs. The formula for the reduced costs is a C bar transpose equal to C transpose minus CB transpose B inverse A. Once again, CB is 0, so this is simply C transpose. So also in the 0th row, we can just copy-paste the coefficients of the objective function. We are now ready to fill in the initial tableau. Here it is. Here we have the negative of the cost of the current basic feasible solution. Here we have the reduced costs, which in this specific case coincide with the coefficients of the objective function. And then in the remaining rows of the tableau, we have here capital B inverse times the right-hand side vector B. And once again, since B inverse is the identity, this is simply the right-hand side vector B. And then we have B inverse A, which again is simply equal to our constraint matrix A. As you can see in this initial tableau, I have added few labels outside of the tableau, namely this x4, x5, x6, and this x1 until x6. These are labels that help us understand what's going on. So the xi's here at the top simply indicate which columns corresponds to which variable. There's nothing special about this. Of course, the first column is x1, the second x2, the third x3, and so on and so forth. These labels are useful to us to be able to quickly identify which column we're looking at. For example, if I look at the column -12, 2, 2, 1, if I didn't have this label, I would have to count that this is the first, second, third column, so it is the one corresponding to x3. Now having the label here instead just allows me to quickly understand that without counting which column this is. Now the labels on the left instead are a little bit more interesting. In fact, they tell us which are the basic variables and in what order. In this example then, I know that x4 is the first basic variable, x5 is the second basic variable, and x6 is the third basic variable. Remember that the 0th column tells me the value of the basic variables in the current basic feasible solution. So in particular, using these labels, I can quickly understand what is the current basic feasible solution. In this case, it is x4 equal to 20, x5 equal to 20, and x6 equal to 20. Now all these labels are not really necessary. In fact, if you didn't have the ones in the top, you can easily write them down. You just need to write x1, x2 until xn. And it's interesting to notice that also the ones on the left are not really necessary, meaning that if you didn't know them, you could recover what they are. And this can be done by looking at the remaining part of the tableau. In fact, we know that the first basic variable, in this case x4, will have the associated column, in this case here it is, the column of x4, which is the first unit vector. And in fact here we have the first unit vector. Therefore I could have just found this unit vector in my tableau. Now this is the column corresponding to x4, and so I look at the row where the 1 is, and correspondingly I will write x4 here. Similarly, the second basic variable corresponds to the second unit vector. So also in this case, I could have found the second unit vector, here it is. This corresponds to the variable x5, so I can write x5 in the row where the 1 appears. Here is x5. And similarly for x6. In any case, in this first example, we will keep all the labels in order to better understand the example. We're now ready to start with an iteration of the full Tableau implementation of the simplex method. The first thing we need to do is look at the reduced costs and see if there's any negative one. In this case, there are 3 negative ones. So in this case, our pivoting rule will tell us which one we should pick. In this example, we don't have any explicit pivoting rule. I will be your pivoting rule, so I will break all the ties as I want. In this case, I decide that we should have x1 enter the basis. So this implies that this is now my pivot column. The vector u then is 1, 2, 2. The next thing we need to do is find the theta star. To do this, we need to form the ratios xbi over ui. We should consider this ratio only for the indices I for which ui is positive, but in this case all the 3 of them are positive, so we need to consider all these 3 ratios. Now to compute xb1 over u1, we can read xb1 here is 20 and u1 here 1, so the ratio is 20. Then xb2 over u2 is 20 divided by 2, which is 10. And finally, xb3 over u3 is 20 divided by 2, which is 10. So these are my 3 ratios. We need to pick the smallest. So we could choose the second or third basic variable to leave the basis, because they both correspond to the smallest ratio. Once again, we have to look at our pivoting rule to break this tie, and since I am your pivoting rule, I tell you to choose L equal to 2, so the second basic variable should leave the basis. This determines the pivot row in green, and accordingly the pivot element, which is at the intersection with the pivot column. Now we also know what the new basis will be. Everything we need to do is replace the second basic variable with x1, which entered the basis. So b bar 1 remains 4, b bar 2 is changed from 5 to 1, and b bar 3 remains 6. Next, we need to compute the new tableau corresponding to the new basis. In order to do that, we need to perform the elementary row operations that transform the pivot column into the column that has 0, 0, 1, and 0. So to have a 0 in the 0th row, we need to multiply by 5 the pivot row and add it to the 0th row. To obtain a 0 here, we need to instead multiply the pivot row by 1/2 and subtract it from the first row. To obtain a 0 in the last row, I simply need to subtract the pivot row from the third row. And finally, to obtain a 1 in the pivot element, I simply need to divide by 2 the pivot row. If you perform all these elementary row operations, you will obtain this new tableau. Note that the first column has become 0, 0, 1, 0 as it should. An important thing to notice is that now I have x1 here instead of x5. This is because now the second basic variable is x1. Accordingly, the column corresponding to x1 is the second unit vector. What else can we see from this tableau? Well, the cost is now minus 100. So we went from a cost of 0 to minus 100. Hence, the new solution is indeed better than the previous one, as it should be. We can also write down explicitly the current basic feasible solution. We will have that x1 is equal to 10, x4 equal to 10, x6 equal to 0, and all the other variables, the non-basic ones, will be 0. So the full vector is this x, 10, 0, 0, 10, 0, 0. We also notice that this is a degenerate basic feasible solution. And this is because the variable x6, which is a basic variable, is equal to 0. In particular, you have a degenerate basic feasible solution if and only if you have a 0 here in the 0th column, except of course for the 0th row. Now we can also visualize our new basic feasible solution in the original three-dimensional problem. Everything we need to do is to throw away the slack variables, and so we're left with the vector 10, 0, 0. 10, 0, 0 is the vector that was called D in the original picture, so here it is. And now we can see geometrically the pivot that we performed. In fact, we started from the basic feasible solution 0, 0, 0, and we moved along an edge of the polyhedron to the new basic feasible solution 10, 0, 0. From this picture, you can also see that this solution is degenerate because there are 4 active constraints in this vector. Before proceeding with the next pivot, I want to remind you that the tableau is a representation of the equality constraints obtained from the original system by multiplying on the left by B inverse. Now we can use our current tableau to obtain this system of equalities that is equivalent to Ax equal to B. In the first equation, we will have 0x1 plus 1.5x2 plus 1x3 plus 1x4 minus 0.5x5 equal to 10. And similarly, you can obtain the second and third constraints, which are written down here. Now, this system of equations is equivalent to the original one, Ax equal to B. We're now ready to get back to the simplex method. We look at the reduced costs. There are 2 negative ones, and the pivoting rule will tell us which one enters the basis. Since I'm your pivoting rule, I tell you that x3 should enter the basis, so the pivot column is this one, and the vector u is 1, 1, minus 1. We now have to look at the ratios xbi's over ui, and we only have to do it for I equal to 1 and 2 since u3 is negative. The ratios are 10 divided by 1 and 10 divided by 1. So they are both 10, and our pivoting rule will tell us which variable exits the basis among these two. Being your pivoting rule, I tell you that we should let L equal to 1 so that xb1 leaves the basis. So x4 leaves the basis, and this determines the pivot row and also the pivot element. Now we have all the information that we need to construct the new tableau. We need to transform the pivot column into the column that has all zeros except in the pivot element where we should obtain a 1. To get rid of this minus 2, we need to multiply the pivot row by 2 and add it to the 0th row. To get rid of this one, we just need to subtract the pivot row from this row, which is the second row. To get rid of this minus 1, we only need to add the pivot row to the third row. Finally, we don't need to do anything in the pivot row because we have already a 1. If you perform all these elementary row operations, you obtain the next tableau, which is the one over here. As you can see, in the column that was our pivot column, we now have the first unit vector as we should have. Correspondingly, we replace x4 here with x3 because x3 entered the basis and x4 left the basis. We can see that now the cost has been reduced to -100 and the new basic feasible solution is 0, 0, 10, 0, 0, 10. Here it is. We can again interpret this basic feasible solution in the original three-dimensional problem. Dropping the slack variables, we obtain 0, 0, 10. So we have now moved to the point B. To recap, we started from A, moved to D, and now we move to B. From the picture, we know that we're not yet optimal, because our optimal solution is E. So let's get back to our tableau. The fact that we're not in an optimal solution is clear from the tableau because we still have a negative reduced cost. -4 is the only negative reduced cost, so we must have x2 enter the basis. So the pivot column is this one. Next, we compute all the ratios xbi over ui whenever ui is positive. So we have 10 divided by 1.5 and 10 divided by 2.5. The smallest of the two is 10 divided by 2.5. So the third basic variable, namely x6, will leave the basis. So the third row is the pivot row, and accordingly the pivot element is 2.5. To construct the next tableau, we need to obtain 0, 0, 0 and 1 using elementary row operations. To obtain a 0 in the 0th row, we multiply the pivot row by 4 divided by 2.5 and added to the 0th row. To get rid of this 1.5, we multiply the pivot row by 1.5 divided by 2.5 and subtracted to the first row. To transform this -1 in a 0, we multiply the pivot row by 1 divided by 2.5 and added to the second row. And finally, to obtain a 1 in the pivot element, we divide the pivot row by 2.5. Performing all these elementary row operations, we obtain this new tableau. In particular, our old pivot column is now the third unit vector, and we replaced x6 with x2 over here, because x6 left the basis and x2 took its place. We can see that the cost has now been reduced to -136, and the corresponding basic feasible solution is 4, 4, 4, and then 0, 0, 0 in the non-basic variables. Here it is. In terms of the original variables, we are now in the point E equal to 4, 4, 4. From the picture, we know that the vector E is optimal. Of course, we can also understand the optimality of this basic feasible solution by looking at the tableau, because all the reduced costs are greater than or equal to 0. So the optimality conditions are triggered and our simplex method terminates. Let's now get back to our three-dimensional picture. Overall, we traced 4 basic feasible solutions. We moved from A to D, then to B, and then to E. Every time we moved along an edge of the polytope. It's important to notice that with different pivoting rules, a different path would have been traced. Now, it is kind of interesting that we traced 4 basic feasible solutions to get from A to E, while in fact it's clear from the picture that we could have moved along the edges of the polytope from A to E only in 2 steps. Namely, we could have gone from A to D and then from D to E. So we can wonder if it is actually possible, with a different pivoting rule, to move from A to E in only 2 iterations of the simplex method instead of 3 as we did. Interestingly, the answer is no. How can you see that? If you remember, in the basic feasible solution A, the variables in the basis were all the slack variables, so x4, x5, and x6. On the other hand, in E, the basic variables are x1, x2, and x3. Now we know that at every iteration of the simplex method, one basic variable leaves the basis, and one that was non-basic enters the basis. So here, to go from A to E, we need to bring in the basis all the three variables x1, x2, and x3 that were not in the basis in A. So we need at least 3 iterations. But this again seems a little bit strange because it doesn't match our geometric intuition. In fact, geometrically it is clear that we could have gone from A to D and then to E. So what if you try to do this with your simplex tableau? What will happen is that in D you need to perform a degenerate change of basis. So this is one iteration of the simplex method which performs a change of basis but doesn't change the corresponding basic feasible solution. And this makes sense because D is in fact a degenerate basic feasible solution as we previously observed. And this concludes our complete example of the full tableau implementation. Now I think we have understood quite well the full tableau implementation, but there's one thing that we still have not analyzed, namely the computational effort per iteration. In fact, we've already seen the computational effort per iteration both for the naive implementation and the revised simplex method. Now we're going to understand it for the full tableau implementation. In this case, it's very simple. In fact, it's clear from the description of the full tableau method that in every iteration we simply need to update every entry of the tableau. And it's simple to see that updating each entry of the tableau only requires a constant number of arithmetic operations. Therefore, the amount of computations per iteration is proportional to the number of entries in the tableau. We have n plus 1 columns and m plus 1 rows. So in total, the number of operations is big O of mn. If you remember, this coincides with the number of operations performed in one iteration of the revised simplex method. So we have now understood that the full tableau implementation and the revised simplex method are the most efficient, while the naive implementation is less efficient. We have seen that both the revised simplex method and the full tableau implementation require big O of mn operations per iteration. The last thing I want to do in this video is to compare these two implementations more in detail. As always, we start from a standard form linear programming problem. Minimize C transpose x subject to ax equal to b and x greater than or equal to 0. To make this comparison, it will be really useful to slightly change the problem. What I want to do is add a bunch of additional variables that are similar to slack variables. Of course, I don't need any slack variable here because I already have equality constraints, but I add them anyway. So I add plus y1 to the first constraint, plus y2 to the second constraint, and so on and so forth. In matrix form, the new system of equations will be ax plus identity times y equal to b. As for real slack variables, I also add the constraints that the y variables are greater than or equal to 0. Finally, I make no change in the objective function, so essentially I'm just adding plus 0 transpose y. Note that these two problems look similar, but are in fact very different. Actually, at this point, I don't even care if they are equivalent or not. What I want to do is to consider this new problem and implement the simplex method on it, with the difference that we never allow any of the components of y to become basic. This means that all the y variables will always be non-basic, therefore y will always be 0. And if y is 0, then the new problem coincides with the old one. So this is admittedly a strange setting. I am constructing a different problem from the original one, but since I will apply to this problem the simplex method in this very restrictive way, I will effectively solve the original problem. Now let's see how the simplex tableau will look like for this strange problem. The equality constraints of the problem are ax plus identity y equal to b. So in my constraint matrix, the first n columns will consist of the matrix A, while the remaining m columns will be the identity matrix. Now we can already write down the simplex tableau except for the 0th row. In fact, in the 0th column, we will have B inverse B, since B is still the right-hand side, and then in the remaining columns, I will have B inverse time the constraint matrix, so the first n columns will be B inverse A, and the remaining m columns will be B inverse times the identity, which is simply B inverse. Let's now compute the 0th row. For the entry in the top left, our formula is always minus CB transpose B inverse B. So the only thing left to understand are the reduced costs. To compute the reduced cost, we always use the formula cost vector minus CB transpose B inverse constraint matrix. Now the transpose of the cost vector is C transpose and then 0 transpose, while my constraint matrix is A and then the identity. So if we look at the first n components of this row vector, we have C transpose minus CB transpose B inverse times A, and these are exactly the original reduced costs, which as always I denote by C bar transpose. The remaining n components are 0 transpose minus CB transpose B inverse times the identity, and here we have it. So now I can fill in also the remaining part of the 0th row. Here I have C bar transpose and here minus CB transpose B inverse. So essentially for this new problem I obtain a tableau in which the first n plus 1 columns give me exactly the simplex tableau that I would have had for the original problem. So the difference consists in the remaining additional m columns that I didn't have in the simplex tableau of the original problem. So now if we follow the full tableau implementation for this new problem with the additional rule that y never enters the basis, I am effectively performing the full tableau implementation on the original tableau. The only difference is that I'm keeping these additional m columns. The reason we're doing this is that in this m by m submatrix, at each iteration I have explicitly the matrix B inverse. And so this construction gives me a nice link between the tableau and the revised simplex, because if you remember, in the revised simplex at each iteration we explicitly constructed the matrix B inverse. We have just discussed how we can visualize the full tableau method applied to the original problem on this extended tableau. And now we're going to see how we can visualize also the revised simplex method on this extended tableau. Now, in every iteration of the revised simplex method, of course we calculate the 0th column, because B inverse B contains the values of our basic feasible solution, while this is the cost of the current solution. On the other hand, in the revised simplex method, we don't explicitly construct this middle part of this extended tableau, but instead we explicitly construct B inverse on each iteration. In the revised simplex method, we also always compute this vector minus CB transpose B inverse, which is our vector of the simplex multipliers. Let's now continue with the revised simplex method, and let's use a pivoting rule that evaluates one reduced cost at a time until a negative reduced cost is found. So essentially we are computing one reduced cost, so one entry of the vector C bar prime. Let's say we compute the first entry. Now if it's greater than or equal to 0, we continue with the next entry and so on and so forth until we find a negative one. Now, when we find a negative one, we need to compute the vector u, which is B inverse aj, which is, in my extended tableau, the vector just below the negative reduced cost that we have just found. So to recap, the revised simplex essentially at each iteration computes the 0th column, it computes B inverse, then it computes the vector p, and then it starts to compute one by one the entries of C bar prime. When a negative one is found, the corresponding column is computed. Notice that, in general, the revised simplex will not compute the full vector of reduced costs, and it will only compute one of the columns of the matrix B inverse A. At this point, we have visualized both the full tableau implementation and the revised simplex method using this extended tableau, and we can discuss the relative merits of the two methods. So now we can use this extended tableau to understand once again how many operations per iteration are performed both in the full Tableau implementation and in the revised simplex. We have already seen this, but let's do it again by looking at this extended Tableau. So the full Tableau method at each iteration updates all the zeroth column and then the n columns that I have written here in gray. So the computational requirement per iteration, and updating each entry takes a constant number of operations. So the computational requirement per iteration is big O of mn. On the other hand, the revised simplex method updates B inverse and the vector of the simplex multipliers. This requires only big O of m square operations because this part of the tableau has m plus 1 rows and m columns. Then the reduced costs are computed. Each one we know requires big O of m operations because it is obtained with the scalar product P transpose Aj. So in the worst case, when we need to compute all of them, we need a total number of big O of mn operations. Then, once we have understood which variable xj should enter the basis, we compute the pivot column B inverse Aj. This is the product of an m by m matrix and an m vector, so it requires big O of m square operations. Therefore, the worst case computational effort per iteration is big O of mn plus m square. Using the fact that m is less than or equal to n, we obtain big O of mn. So far, nothing new. However, things start to look very different if we don't look at the worst case, but we look instead at the best case. In fact, if we are lucky in the revised simplex method, already the first reduced cost that we compute is negative. In this case, we only computed one reduced cost, which only required big O of m operations, instead of the big O of mn that we needed in the worst case to compute all of the reduced costs. So in the best case, the total number of operations per iteration is big O of m square, instead of big O of mn. So while in the worst case, both the full Tableau implementation and the revised simplex method require big O of mn, in the best case, the revised simplex method requires fewer operations, namely big O of m square, while the full Tableau implementation is stuck with big O of mn. This means that the revised simplex method cannot be slower than the full Tableau method, but it could be much faster during many iterations. Another important advantage of the revised simplex method is that the memory requirements are big O of m square, while in the full Tableau they are big O of mn. In fact, in the full Tableau method, in each iteration we keep the full Tableau, which has m plus 1 times n plus 1 entries. So we're keeping big O of mn entries. On the other hand, in the revised simplex, we fully compute only the 0th row and the blue part over here. And this amounts to big O of m square entries. Then when we compute the reduced costs one at a time, if we obtain a reduced cost that is greater than or equal to 0, we don't need to keep it in memory, we can just erase it. And when we find a negative one, we explicitly construct only one column of B inverse A, which consists of only m entries. So essentially, this decrease of memory requirements comes from the fact that we don't explicitly construct B inverse A. And notice that, regarding memory requirements, this difference from the full Tableau to the revised simplex doesn't happen only in the best case, but happens in any case. I should mention at this point that in real-world problem n is often much larger than m, so the difference between big O of mn and big O of m square is often significant. At this point, if you stop and think for a minute about what we just said, I'm sure you will have a question. Namely, how is it possible that the memory requirement is big O of m square, where even just storing the input of the problem requires big O of mn? Simply because the matrix A is m by n. And you would be absolutely right. For a general linear programming problem, you need a big O of mn just to store the matrix A, even though later, with the revised simplex method, at every iteration you only need to update big O of m square numbers. However, from a practical perspective, we never need to store big O of mn entries, even though the matrix A is m by n. The reason is that in most large-scale problems that arise in real-world problems, the matrix A is very sparse, meaning that most of its entries are zeros, and so it can be stored in a compact way. In order to do so, you can simply store every non-zero entry of A together with its corresponding row and column. The number of numbers that you have to store in this way is simply 3 times s, where s is the number of non-zero entries in A. Okay, so at this point we used the sparsity of the matrix A to argue that the memory requirement of the revised simplex is in most cases much lower than big O of mn. But at this point you could wonder if the sparsity of the matrix A can also be used to decrease the memory requirements for the full tableau method instead. Unfortunately, that's not the case. And again, the reason lies in the fact that the full tableau explicitly constructs B inverse A. Now, even if we assume that A is sparse, so that it has few non-zero entries, the matrix B inverse A in general will not be sparse. So the sparsity of A doesn't help in the full tableau. In these last few slides, we discussed many things about time and memory requirements of both the full tableau and the revised simplex. So let's just summarize them in this table. In this column, we have the full tableau, and in this other column, we have the revised simplex. Then we consider worst case and best case, time and memory. Now for the full tableau, everything is big O of mn, both the number of operations per iteration and the memory requirement, and it doesn't matter if we're considering the worst case or best case. On the other hand, for the revised simplex, in the worst case, both time and memory are big O of mn, matching the full tableau. However, in the best case, for the revised simplex, both time and memory decrease to big O of m square. So all in all, full tableau and revised simplex have very similar requirements in the worst case, but in the best case, the revised simplex is better. This is why among the 3 implementations that we have seen, the revised simplex is the most efficient, both in terms of time and memory. And with this table, we conclude our video on the different implementations of the simplex method.